Hello and welcome to lecture 30. So, in last lecture we were discussing about say two spool configuration with unmixed kind of flow, where fan and compressor they are on the same shaft, and that is what has been routed by LP turbine, and for that we have solved a numerical for the ground condition with entry pressure and entry temperature, and we have done our calculation for the net thrust, thrust specific fuel consumption, propulsive efficiency, thermal efficiency and overall efficiency. So, let us move forward now. So, we know we are looking for the performance parameters calculation in terms of thrust or specific thrust, thrust specific fuel consumption, fuel air ratio, propulsive efficiency, thermal efficiency, overall efficiency. And for this turbofan engine, this is mainly been depending on different cycle parameters. Very first that we say is a overall pressure ratio or compressor pressure ratio, where we are having fan pressure ratio, LP compressor pressure ratio, HP compressor pressure ratio. By changing the pressure ratio of any of the one, that will be changing the performance parameter of the engine. The next parameter what we have is bypass ratio, that is a speciality of the turbofan engine. We have turbine entry temperature, that also we have seen for turbojet engine as well as for the turbofan engine, that has great impact on parameter called efficiency. We have assumed different efficiency of different components, which include diffuser, fan, compressor, combustion chamber, turbine, nozzle. This also have impact on the performance of the engine. And here for this case we are discussing about the ground condition. It may be possible that we can do our calculation for the flight condition at particular altitude. So, let us try to look at what all are our performance parameters. Suppose if I consider we have the effect of fan pressure ratio, putting compressor pressure ratio, that means HP compressor and LP compressor pressure ratio, turbine entry temperature, bypass ratio and mass flow rate to be constant. We will be changing only the fan pressure ratio. So, when we are changing our fan pressure ratio, very first parameter of our interest, it is our thrust. So, here in this case if we look at carefully, it says when we are increasing our fan pressure ratio, my cold thrust, that is what will be increasing. This increase is because of my exit velocity from the nozzle will be higher. At the same time, the hot thrust, that is what will be reducing here, and this is because in order to rotate my fan or in order to generate that pressure ratio, large amount of work, that is what is required, and that is what will lead to reduce the enthalpy at the exit, and that is the reason why our thrust, hot thrust, that is what will be reducing with the increase of fan pressure ratio. In overall sense, if we are considering this as our engine, for that our thrust, that is what will be increasing with the increase of fan pressure ratio. Now, the next parameter what we have here, it is our say specific thrust. Since my specific thrust, it is a function of say thrust divided by my overall mass flow rate. This mass flow rate is constant, and that is the reason why my specific thrust will be increasing with the increase of fan pressure ratio. Now, let us look at the parameter called thrust specific fuel consumption. So, for this thrust specific fuel consumption, we can say with increase of the fan pressure ratio, we are having the thrust specific fuel consumption, that is what will be reducing. So, just realize this as a case. Okay. Now, let us look at what is happening with our efficiency point. So, since our velocity is 0, that is the reason why propulsive efficiency is 0 and our overall efficiency will be 0. So, we are able to calculate only thermal efficiency. So, it says with the increase of fan pressure ratio, the thermal efficiency will be increasing. okay, and that is what will be increasing up to certain point, and then we will be having say with change of fan pressure ratio, our efficiency will remain nearly constant. Okay. Now, let us take the next parameter what we have. We have our fan pressure ratio that is constant, and my LP compressor pressure ratio I am varying. So, under that configuration it says by changing the LP compressor pressure ratio, my cold thrust that is what will not be changing, but the hot thrust that is what will be reducing. In overall sense, if we look at my total thrust that's or net thrust, that is what will be reducing with the increase of LP compressor pressure ratio. Here again you can correlate that in terms of say the exit velocity, and you can correlate that with the fuel air ratio. Okay. Now, in order to understand what is happening with the specific thrust, my thrust is reducing with the increase of LP pressure ratio. That is the reason why the specific thrust also will be reducing with the increase of LP pressure ratio. So, just look at this is giving us idea about what need to be the LP compressor pressure ratio. Again, this is for the fixed value of fan pressure ratio, turbine entry temperature and bypass ratio. Suppose one of the parameter if we consider that is what is higher, then accordingly my thrust will be changing. Okay. So, you cannot say this as a generalized case, this is for the specific number what we have mentioned here. Okay. Similarly, let us look at what is happening with the thrust specific fuel consumption. So, it says the thrust specific fuel consumption that is what will be reducing with the increase of LP compressor pressure ratio. Though here my thrust that is what is reducing, but at the same time in order to increase my pressure ratio, the amount of fuel requirement will be larger, and that is the reason why it is reflecting here. And we can say this is representing the increase of thermal efficiency with the LP compressor pressure ratio. Okay. Now, let us look at what is happening with my HP compressor pressure ratio. Can you guess what will be the change here? If we are putting our fan pressure ratio, LP compressor pressure ratio, turbine entry temperature, bypass ratio and mass flow rate putting constant. So, under this configuration we will see we will not be having major change in the cold thrust, but the hot thrust that is what will be reducing. Again, this is what is in relation with the work developed by the engine, both for say our HP turbine as well as for the LP turbine. So, that is where this change that will be coming with. And here if we look at my specific thrust, that is what will be reducing with the increase or say of my HP compressor pressure ratio. This is representing similar to what we have observed for say fan pressure ratio, LP compressor pressure ratio. With the increase of HP compressor pressure ratio, the thrust specific fuel consumption that is what will be reducing. Let us look at what is happening with the efficiency. It says when I am increasing my thrust specific when I am increasing my HP compressor pressure ratio, our thermal efficiency that is what will be increasing with. Now, the situation is what is our requirement? Very first thing we say we want to improve the efficiency. When I say I want to improve the efficiency, suppose say I want to improve my thermal efficiency, then this is giving us idea that you go with increasing the pressure ratio. Okay. Be careful here, our overall pressure ratio we are maintaining to be same. Okay. Now, let us move towards the next case where we are discussing about the bypass ratio change. When we say when we are increasing our bypass ratio, with the increase of bypass ratio, my cold thrust that is what will be increasing, but at the same time the hot thrust that is what will be reducing drastically with the increase of bypass ratio, and that is what is reflecting in terms of reduction of the thrust. Okay. since my thrust is reducing, the specific thrust also will be reducing in the sense for the constant mass flow rate configuration. And here in this case, if we look at my thrust specific fuel consumption also will be reducing with the increase of bypass ratio. Let us look at what is happening with the efficiency term. It says by increasing the bypass ratio, we have our thermal efficiency, that is what will be improving. Okay. Now, again be careful, this is what is with the fixed number of this particular engine. Okay. Now, you can play with some parameters. Suppose you will be having question, sir, if you will be increasing the turbine entry temperature, will it be same? Let us look at that part. So, we have our next parameter, it is turbine entry temperature, and for this turbine entry temperature, it will not be changing my say cold thrust, but with the increase of turbine entry temperature, my hot thrust, that is what will be increasing, and it says it will be giving the rise of total thrust or the net thrust. Okay. That is what will be reflecting in terms of specific thrust to be higher. Okay. And here, since we want to increase the turbine entry temperature, the amount of fuel need to be added will be higher, and that is the reason why the thrust specific fuel consumption will be increasing with the increase of turbine entry temperature. Now, in terms of efficiency, again since my amount of fuel need to be added, that is higher, that is what will be reflecting the reduction of the thermal efficiency with the increase of turbine entry temperature. So, we can say in order to improve the thrust or total thrust, we can go with increase of turbine entry temperature, but that will be at the cost of your fuel consumption, and that will be at the cost of your thermal efficiency reduction. Okay. Now, let us look at what is happening with change of the mass flow rate. So, if we consider if we are increasing the mass flow rate, this mass flow rate is a function of my bypass ratio for the core engine as well as for the fan. So, that is the reason with the increase of mass flow rate, we have increase in hot thrust as well as increase in cold thrust. In overall, we can say our net thrust, that is what will be increasing. But at the same time, when we are discussing about say thrust specific fuel consumption, that is what will remains constant. Similarly, if we are discussing about say the change of nozzle area, since my mass flow rate is higher, with increase of the mass flow rate, my nozzle area will be larger in order to handle that mass flow rate. Okay. And if we look at the thermal efficiency, it almost remains constant with the increase of the mass flow rate. Okay. So, we can say we can move with the increase of mass flow rate, but as we have discussed, in order to handle that large mass flow rate, your dimensions will be changing, your diameter will be larger. Suppose if you are putting other parameters to be constant, under that configuration your drag will be increasing, and that is what will be reflecting in terms of your specific fuel consumption. Okay. So, these all are the parameters, performance parameter, and their impact on thrust, specific thrust, thrust specific fuel consumption, and for the ground condition we are more concerned with the thermal efficiency. Okay. So, similar numerical you can solve for the flying condition also, and that is what will be giving you idea what will be the effect of these parameters on say performance. Okay. So, for this particular configuration we will be discussing for say ground condition only. Now, let us move towards the next configuration. So, what all we have discussed? We have discussed the unmixed single spool configuration. We have started discussing about the two spool configuration, in which fan and low pressure compressor they are on one shaft. Now, let us move to the next step, that where we are having the fan, it will be driven by LP turbine, and the compressor or the compressor stages that will be driven by HP turbine. So, I am giving you time, just try to plot the line diagram for this kind of configuration, where fan will be rotated by LP turbine and compressor that will be driven by HP turbine. Let us see how your line diagram will be. Okay. So, let me put this as a line diagram here. What it says, this is my inner spool, or we can say my LP spool. That is what is used to rotate only fan. Okay. So, we are having this LP turbine stage, that is what is connected with the fan. All my compressor stages that will be rotated by our HP turbine. Okay. I am sure you are able to understand this part. Here it is written fan or fans. So, it is not always that we will be having single fan. Suppose if I consider we are having say low bypass ratio engine, in which we will be having multiple fan stages. So, that is the reason why it is written as fans. So, such configuration it is existing for GE Rolls-Royce F316 engine. So, you can say this is low bypass ratio engine, in which we are having fans in place of single fan. Okay. Can you plot the TS diagram for this cycle? So, let us look at how your TS diagram will be looking like. So, here we are having our entry pressure. Very first component we have is our intake. This is representing the actual process. Next we have is our fan, that is what is rising the pressure from P02 to P03. This is representing my actual process from 2 to 3. The component we have is for rising the pressure from P03 to P04 is our compressor stage. So, this is representing the actual process from 3 to 4. We have our combustion chamber, and that is what will be rising the temperature to T05 with some drop of pressure from P04 to P05. We have our HP turbine, that expansion process is represented by process 5 to 6. The next component what we have is our LP turbine. This LP turbine process it is represented from 6 to 7. We can have our tailpipe, that is where we will be having drop of pressure, which is represented from P07 to P08. The temperature, that is what will remains constant. So, T07 and T08, that is what will be same. And this is representing the expansion which is happening in the turbine nozzle from the process 8 to 9. Similarly, here in this case we have our another nozzle, that is with the fan, and this expansion it is been represented from process 3 to 10, and this is representing the expansion process. So, if you look at in clear way, this diagram is similar to what all we have discussed in the earlier case. Okay, but be careful, here we are having different engine configuration, where my LP turbine it is used to rotate only fan, and all my compressor stages they are being rotated by the HP turbine. Okay. So, let us look at, so this is representing the cut section of F136, where we are having number of say fan stages. So, here we can say it is a first stage of fan with a white cord blade, and here these are the other stages. This white cord blade that they are having the special benefits in terms of say foreign object damage, and at the same time it has the aerodynamics benefit also. In other stages, if you look at, they are having say different kind of blade design. Those who are interested in doing the design for such kind of compressors, fans, LP compressor, HP compressor, you can go with say the special designed course on aerodynamic design of axial flow compressors and fans. That is what will be giving you idea how these blades they are been designed, how these numbers they are been selected, how the shape of this blade, that is what is been decided with. In later case, if you look at these are the HP compressor blades, that is what will be rotated by say HP turbine, and these fans that will be rotated by the LP turbine. And here this is representing the engine, that is what has been applied with the most recent aircraft, it is F-35, and that is what is flying at say supersonic speed. Okay. So, now let us try to understand the actual cycle analysis for this. So, very first process we are configuring is say my inlet process or intake process. For that we have information about our diffuser efficiency. From this diffuser efficiency formulation, we can calculate what will be our exit pressure and what will be our exit temperature from the intake. So, this information that is what is required for the calculation, or that is what is say our inlet condition for the fan. Okay. Now, let us move with the forward fan configuration. That process we are representing as say 2 to 3. Say for this we may be aware of fan compression ratio. We know what will be the fan efficiency. Again, this fan efficiency basically we are assuming. Okay. Initially we are assuming, and then after making the testing of this fan, we will be coming up with the verification whether what all efficiency we have assumed is it coming same or not. Okay. So, it is all the way different ball game. Same way for intake also, you will be assuming your intake efficiency, and then after you will be doing your design for the intake, and then you will be going with the computational study or experimental study, and you will be verifying what efficiency number you have assumed, is it coming same or not. So, basically you are targeting this efficiency, you want this efficiency to be achieved. Okay. So, from this we will be doing our calculation for the temperature ratio, that is in the form of pressure ratio as well as the efficiency, and from that we will be calculating what will be our exit pressure and exit temperature from the fans or fan. Okay. Now, next component what we have is our compressor. This compression process we are representing between 3 to 4. Be careful, here we are not having LP compressor or HP compressor, it is straightway it is compressor. Okay. So, this compressor pressure ratio we can write down, it is P04 by P03. We know what is our compressor efficiency. Based on that we will try to calculate what will be the exit pressure and exit temperature from this compressor. Okay. Now, let us look at the next component we have is our combustion chamber, and for this combustion chamber we have our entry conditions known to us. Okay. We have drop of pressure which is happening in the combustion chamber, that is what will be giving the exit pressure from the combustion chamber, or we can say that is what is the entry pressure to my turbine. Okay. And if we will be doing our energy balance, we will be able to calculate what will be our fuel air ratio for this particular engine configuration. Now, let us try to do this calculation as we have discussed for the fuel air ratio. Again, be careful what numbers are given. It may be possible that you are given with the fuel air ratio and you need to calculate what will be the turbine entry temperature, or maybe turbine entry temperature is given to you, you need to calculate what will be my fuel air ratio. Okay. Now, let us try to look at, suppose say this engine in which we will be having the bleed. Okay. So, at some location say P03B, at some temperature T03B, we have the air, that is what is being bleed with. So, that is the reason why For the combustion chamber, my entry condition that is given by m dot core into 1 minus B H04. Same way, since the amount of air it is been bleeded from the compressor, that is the reason the exit condition will be m dot core plus m dot F minus m dot B into H05. So, if this is the case, we can write down our energy balance. So, carefully read the instruction what is given, whether it is given with the bleed or it is non-bleed. If it is not given in terms of any bleeding, please do not assume any number for this bleed air. Okay. So, here if we will be doing our energy balance, and if you compare your equation, you will be having the change in the formula for the fuel air ratio, that will be in terms of multiplication of 1 minus B. Okay. Now, the next component what we have is our turbine. So, again be careful what configuration it is given to you. Here it is written, this HP turbine it is used to rotate only compressor stage. Okay. So, if that is the case, we can write down our work balance. Here in this case, we are not considering anything in terms of bleeding. So, that is the reason why my formulation will be m dot core into 1 plus F. Okay. And this is representing our temperature ratio. So, we can calculate what will be the temperature at the exit of the HP turbine. Since we know what is our efficiency, based on this efficiency we can calculate our expansion ratio, or we can say our pressure ratio. From that we will be calculating our exit pressure and exit temperature from the HP turbine. Now, let us try to look at, suppose if we are having the bleed kind of configuration, can you write down the equation for the work balance? Let us see how good you are in terms of your understanding here. So, here we are writing the equation for the work balance. This work balance equation you can understand the formulation that will be changed here with minus B here. Same way in the case of the compressor also, since we are extracting the work at some location T03B. So, write it carefully. Here in this case the formulation after T03B it will be with 1 minus B. So, do not get confused. Okay. Now, here if this is the case, so just realize this part, after T03B the amount of air, that is what we have bleeded, that is the reason why my mass flow rate that will be m dot core into 1 minus B. Okay. If this is the case, we can do our calculation for the exit temperature from the HP turbine. Based on the efficiency formulation, we can calculate what will be the exit pressure. So, we can have exit pressure and exit temperature with the bleed configuration. Okay. Now, similarly, we can do our calculation for the LP turbine. Say here we are not having any bleed configuration. So, it says my LP turbine, that is what is used to rotate my fan. So, I can write down my energy balance or the work balance here. So, here it is in terms of T06 minus T07. So, be careful, this is representing my LP turbine expansion work. And for the fan, here we are writing in terms of m dot fan. Okay. So, this formulation if I will be putting, then it says my work balance that will be coming in terms of T06 minus T07, and here this is what is in terms of T03 minus T02. So, by this formulation we can do the calculation for the exit temperature from the LP turbine, and based on the efficiency formulation we can calculate what will be the exit pressure from the LP turbine. This is with no bleed configuration. Okay. Suppose say if we will be having the bleed, we know our energy balance, my work balance for the LP turbine and fan, that is what will be going to change. let us see what will be the change. Here, as we have discussed, we will be having this term, that is what will be getting added up. Okay. And if we will be writing the equation, we will be having the denominator, it is 1 plus f minus b. Be careful here. Okay. So, we will not be having any change in terms of the equation for the pressure ratio, but if we will be considering with bleed, my T07, that is what will be different, and that is what will be reflecting in my pressure ratio calculation, and that is what will be reflecting in terms of calculation for the exit pressure and exit temperature from the LP turbine. Now, as we have discussed, we can have our tailpipe. So, for this tailpipe, we can do the calculation for the exit pressure from the tailpipe and exit temperature of the tailpipe. The components what we have next, they are say fan nozzle and the turbine nozzle. So, for this we need to do the calculation for the critical pressure ratio, and we need to compare this critical pressure with the atmospheric pressure, and from that we need to decide whether our nozzle is choked or unchoked, and that is what will be the deciding parameter, what will be the exit pressure from the nozzles, both the nozzles, turbine as well as our fan nozzle. Okay. So, let us put for the fan nozzle, say this as our turbine nozzle. So, this process we are representing in terms of say 0, 8 and 9. So, we can write down the critical pressure ratio as P08 by Pc. Be careful here, this is my nozzle efficiency for the turbine, and the specific heat ratio we are writing as say gamma h, and we will be comparing whether my critical pressure is coming in comparison with the atmospheric pressure. Suppose if I consider my critical pressure is lower, we can say our nozzle is unchoked nozzle and the exit pressure will be the atmospheric pressure. Based on that, we will be doing our calculation for the static temperature, and from that static temperature we will be doing our calculation for the exit velocity. Similarly, suppose if I consider the critical pressure is greater than the atmospheric pressure, under that condition we can say our nozzle is choked nozzle and exit pressure will be the critical pressure, and we can say based on this we can do our calculation for the temperature ratio, we can do the calculation for the static temperature from the nozzle, and by that we will be doing our calculation for the exhaust velocity. Okay. Now, for the fan we can write down similar equation. Here this critical pressure ratio is P03 by Pc. Similarly, this will be my nozzle efficiency for the fan, and specific heat ratio is gamma here, not gamma suffix h. So, we will be doing our comparison, and based on that we will try to calculate the exit pressure and exit temperature. That is what will be helpful to us for the calculation of our exit velocity from the fan nozzle. Okay. Once we have done all this calculation for the cycle parameters, we have done the calculation for the velocity, the next step for us will be to calculate the performance parameter, and those performance parameter we are writing down in terms of net thrust or the total thrust. That is what is my cold thrust and hot thrust. Now, you are matured enough in order to understand what we mean by with bleed configuration and without bleed configuration. If I am moving with the bleed configuration, this formulation that is what will be changing with minus B. Same way you can do your calculation for the thrust specific fuel consumption. We can do our calculation for the propulsive efficiency in the terms of my beta. We can do our calculation for the thermal efficiency. For all these cases, we need to be very careful in terms of whether the bleeding is given or not. Okay. So, once we calculate our propulsive efficiency and thermal efficiency, we can do our calculation for the overall efficiency. Now, here you may get the question saying, sir, for turbofan engine we are discussing about the bleed. Do we have this bleed for turbojet engine also? The answer is yes. There are engines, turbojet engines, where the air it is being bleeded for the special requirement. So, maybe for this week you can do your calculation for single spool turbojet engine, 2 spool turbojet engine. There you can try to put this extraction of the air or bleeding of the air. Okay. So, earlier engines they were not having that kind of configuration, but yes, for recent turbojet engines which is used for the special purpose where the bleeding it is being done. Okay. Now, let us take the numerical here. Say this you will be solving, and the solution for this we will be discussing in the next lecture. So, let us see, we have 2 spool turbojet engine in which the information that is given, say fan pressure ratio is 1.6, compressor pressure ratio is 20. You can say here this is giving you idea that your fan that will be routed by your LP turbine, and overall compressor ratio is given, that means your whole compressor that will be routed by your HP turbine. So, this is also one of the indication. So, do not ask the bifurcation of HP compressor pressure ratio and LP compressor pressure ratio, because it is given in sense say overall compressor pressure ratio. Okay. So, this is the hint here. Now, it says the bypass ratio is 5.6, turbine entry temperature is given 1573 Kelvin, total pressure loss in combustion chamber is 3%, the heating value or calorific value of the fuel is 42,800 kilojoule per kg. The total mass flow rate to the engine is given 120 kg per second. Be careful, this is not the core mass flow rate. So, it is something else, like you cannot or we cannot solve the numericals monotonously. So, we need to bring the changes. So, these are the changes here. It says the bleeding it is been done. Oh, okay. So, bleeding it is done at 500 Kelvin and the pressure is 261.42 kilopascal. Okay, and this bleeding is 20% of core mass flow rate. Okay, so read the instructions carefully. Same way, the isentropic efficiency of the components are say 98% for the diffuser, 88% for fan, 84% for the compressor. Combustion chamber efficiency is 96%, turbine efficiency is 94%, nozzle efficiency is 95%. So, what we need to do is we need to do the calculation for the exit velocity from both the nozzles. We need to do the calculation for the thrust specific fuel consumption, thermal efficiency, propulsive efficiency and overall efficiency. So, you are clear with what configuration we are discussing at this moment. Okay. So, let me give you the hint how do we proceed with. So, component what we have is our intake. For this intake the diffuser efficiency is given, flying condition is given, that means temperature and pressure for this configuration is known to you. So, you can calculate what will be the exit pressure and exit temperature from the diffuser or the intake. The next component we have is fan. For fan, say pressure ratio is given and efficiency is given. So, you can calculate the exit condition from the fan. We are given with the compression process, and for that compressor efficiency and pressure ratio they are given to us. So, we can calculate what will be the exit temperature and exit pressure from the compressor. we have our combustion chamber. For this combustion chamber, the efficiency is given, total pressure loss is given, turbine entry temperature is given. You are given with the bleed, be careful here. You are also given with, say, what is our calorific value of the fuel. So, based on that, we can do our calculation for the fuel air ratio and what will be the exit pressure. The component we have is HP turbine. For HP turbine, the efficiency is given. Again, be careful, the bleed is given. So, in terms of calculation, you need to incorporate this parameter. So, that is what will be giving us the exit pressure and exit temperature. So, exit temperature we can calculate based on our work balance, and exit pressure we will be calculating based on our efficiency equation. Now, we have our LP turbine. This LP turbine basically is used to rotate our fan only. So, that is what will be giving us the number in terms of exit pressure and exit temperature. We have our turbine nozzle. For this turbine nozzle, the efficiency is given. We will be doing our calculation for the critical pressure ratio. That is what will be giving us the number in terms of exit static pressure, exit static temperature, and we can do our calculation for the exit velocity from the turbine nozzle. Similarly, for the fan, we have our information about, say, efficiency of the fan nozzle. We have our bypass ratio. We can do our calculation for the critical pressure. Based on that, we will be doing our calculation for the static pressure, static temperature, and the exit velocity from the fan nozzle. Once we have all these parameters, we will be doing our calculation for the performance parameters. So, I am sure now you have understanding of what configuration we are discussing at this moment, where my fan will be rotated by the LP turbine and all my compressor stages they are being rotated by, say, HP turbine. And here specifically, in order to understand what is the effect of air bleeding, we have taken this as a specific or special numerical. So, here we are stopping with. In next lecture, we will be discussing the solution for this numerical. We also will try to discuss the effect of various cycle parameters on the performance parameter, and we will move forward with the further discussion. So, thank you very much. We are stopping here, and it is preferred that you try to do the solution for this numerical. That is what will be building the confidence for you in order to do the cycle analysis for such configurations. Thank you very much.